Okay, so here we've got a hydrocarbon, and we've been told that it's got an empirical formula of C₅H₈, and we've been asked to work out what the molecular formula of this hydrocarbon is, and we've been presented with also the molar mass of the actual molecule, right? Okay, so how am I going to approach this? Well, one of the things to consider is the fact that, okay, well, what let's define our terms that we're working with. So we've got the empirical formula. We've been asked to work out the molecular formula. So the empirical formula is the simplest whole number ratio of the atoms of the different elements present in the compound, right? Or some would say the smallest whole number ratio. Now, the molecular formula we know to be the actual number of atoms of each element present in the compound or in the molecule, right? So here we're trying to go from empirical to molecular, but we don't have the formula for the molecular, right? That's what we're trying to figure out. But we do have its molar mass. So to bridge that gap, one of the things that would help is to be able to get a comparison between the molar mass of the empirical formula and the molar mass of the molecular formula, and we only have one. So let's try and first thing I'm going to do is I'm going to try and get the molar mass of the empirical formula, right? So we know the empirical formula. It says C₅H₈, right? So in effect, I'm gonna I'm gonna get the mole. I need the molar masses of the constituent elements, right? So in this case, it's a hydrocarbon. The constituent elements are carbon and hydrogen. You may already know what the molar masses of those elements are, but nonetheless, I'm going to go through the process of effectively referring to the periodic table and going from there, right? So hydrogen, we've got effectively the relative atomic mass is the molar mass in this case. So for hydrogen, we've got 1, and for carbon, we've got 12, right? So what I'm going to do, I'm just going to write this here. So the MR, so that's the molar mass of the, let's do carbon first, right? So molar mass of carbon is going to be 12.0. So 12.0, and that's going to be in what units? It's going to be in grams per mole, okay? And similarly, the molar mass for the hydrogen, right, is going to be 1.0 grams per mole, okay? Right. Okay, so effectively what I'm going to do with these values is, if we now get the number of each of these, right? So the number of carbons, the number of hydrogens, and multiply those by their molar mass, and then sum that for each of the elements. That gives us what? So that's going to be 12 multiplied by, here we've got effectively a coefficient associated with the 5, associated with the carbon is 5, right? So 12 times 5, and then add the hydrogen element, which is going to be well, the hydrogen using the word element in this context can create some confusion, but adding the hydrogen component, 1 multiplied by 8, right? So if you have a go, work out what you get for that, and then we'll go from there, right? So okay, so if you did have a go on your calculator, you should have found that this gives 68, okay? And so therefore we can say that the molar mass of our empirical formula, right, MR of C₅H₈ is equal to 68, and then we're going to add our units, grams per mole, okay? Right. Now, as I said at the beginning, what we need to do, or what I'm trying to do, is figure out, well, what's the difference when we compare the molecular formula's molar mass and the empirical formula molar mass. What's the difference, right? So and I'm looking for a multiplier. How to scale up, what number connects the two in terms of a scale up, right? So how am I gonna do it? Well, I'll use a formula. So what I'm gonna use is a formula. I'll use multiplier, and I'm gonna abbreviate slightly, but I'll explain the abbreviations. Multiply is equal to the effectively the MR of the molecular, right, divided by the MR of the empirical. Okay. In effect, this is to say that to get the multiplier, what I need to do is divide the molar mass of the molecular formula by the molar mass of the empirical formula. And at this stage, we've got both, right? So for this one would be the 272, and this one would be the 68, which we worked out, right? So that would be equal to 272 divided by 68 in this case, right? And so if you have a go at that, you would be able to then find out, well, what's our multiplier, right? And in this case, if you did have a go, you'd find that the multiplier is 4. So if you take the empirical formula and you multiply its molar mass by 4, you get the molar mass for the molecular formula. And so I'm now going to use that multiplier to scale up the empirical formula to get the molecular formula. And that would effectively consist of me taking the, okay, so let's start with the carbon, right? So for carbon, what does that mean? That means we're going to take 5 and we're going to multiply that by 4. Of course, that gives us 20, right? And that therefore means that for carbon, the associated number, the associated coefficient there would be 20, right? So it's going to be C20. And if we do the same thing for hydrogen, right? So hydrogen, not carbon. So if you do the same thing for hydrogen, effectively you're going to have 8 multiplied by 4, right? And what does that give you? Well, that's going to give you 32, okay? 32. Right, and that's effectively going to give us H32, right? And if we consolidate this now to form what the molecular formula is, we get C20H32. Okay, so in this case, this is actually what our molecular formula is going to be. Now, this particular molecular formula actually is the molecular formula for quite a range of important molecules, right? And I'm going to take a look at that now. So if we take a look over here, so I put together a diagram which kind of goes into some of this, right? And this family of molecules is effectively called the diterpenes, right? And diterpenes effectively have a general formula of C₅H₈N. So you can see it here. If you look here, you can see it. We've got C₅H₈N. But specifically for diterpenes, what defines it is not just that formula is for terpenes, right? So it's that relates to terpenes. They have a formula of C₅H₈N in this specific case where N is greater than or equal to 2, and N is, this basically just means when N is an integer, right? So when N is equal to an integer, right? So that Z's like is an integer. Now for diterpenes, the typical formula is when N is equal to 4, right? In our question where we looked at the molecular and the empirical formula, we did see that the empirical formula was C₅H₈, right? So if we briefly go back to that, you can see the empirical formula was C₅H₈, right? And then we multiplied it by 4. Now diterpenes by definition effectively is when n is equal to 4. And so they have the molecular formula, effectively what we calculated, C₅H₈. And it's quite a number of interesting molecules which effectively have that formula. So we've got taxodiene. So this particular one, it's all of these are naturally produced, right? Taxodiene is naturally produced in yew trees. So the Pacific yew tree produces it, and it produces it using an enzyme called taxodiene synthase, right? You can look into that, but it's actually quite an important molecule because it's an intermediate which is used to produce Taxol, right? So I'll just write that down to Taxol. This is not Taxol, by the way, but it's an intermediate on the way to produce Taxol. Taxol. And if you search that, all you find is that Taxol is actually a very important anti-cancer drug, right? For treatment, it's a medicine used to treat a various number of cancers. And Taxol was actually added by the World Health Organization to the list of essential medicines back in 2011, right? So that list is effectively, it's a list which has existed since 1977, and it's updated roughly every 2 years, right? Okay, so we've got laurinine, and this also has the same molecular formula, so C₅H₆, and that's naturally produced by a specific type of tree in New Zealand, a conifer tree in New Zealand. And sturmarine, which is here, sturmarine is also naturally, well, as I said, all of them are naturally produced, but this one is naturally produced in like Asian rice, right? So Asian cultivated rice effectively it naturally occurs in that. Okay, and we have beta araniosin, right? Now, as I said, all of these have the formula C₅H₆. So in some sense, we could say they are, I won't go too much into isomerism, but you could say they are isomers of each other in a sense. This is naturally produced by a fungi, a very small fungi, microscopic fungi called Sordaria araniosa, right? And we've got sembrine A, right? So this, again, same formula, C₅H₆, and it's produced by termites as a pheromone, like it's produced as a pheromone by termites, and some pine trees also produce it. And then we have entcorine. Now entcorine, if you study A-level biology as well, so if particularly in effectively the year 2 of, I think some courses it would be in the year 2 of A-level biology within plant biology. So well, not this particular molecule, but it's effectively used to produce by plants. A whole very wide range of plants use entcorine to produce a molecule which you would come across in year 2 plant biology, which is called effectively gibberellins, right? And if you've come across gibberellins, you'd know that they're quite important within plants for things such as cell division and also cell elongation, right? And then the final one I've got here, and by the way, these are not all of the diterpenes. This is just like some of them. It's like I'm not going to include all of them, but this is number one, caspine, right? And caspine is also naturally produced. So this is a molecule, again, C₅H₆, H32, same molecular formula. And this is naturally produced by the castor bean plant. Specifically if the plant is like stressed. So if it's stressed, or if it gets infected, usually this would like trigger the production of caspine within the plant. And that's produced by an enzyme called caspine synthase. A lot of these molecules you're seeing here, the actual molecule which is used by these different enzymes I've mentioned to produce these molecules, in many of the cases it's actually the same molecule that it starts off. But you can look into that. I'm not going to go into all of those details, but you can look into that in your own time to find out, well, what enzyme, what molecule does the enzyme interact with to produce some of these various molecules. But yeah, this is one example of where in nature you can see the actual idea of functional, or effectively functional isomerism play out, where you've got effectively the same molecular formula, but then actually when you look at the actual structure, it can be very, very different across the different molecules with the same formula. Okay.